Hi, with this video lecture, I'm going to start your chapter number 5, which is about heat treatment of steel. So hence in chapter number 4, which was our last chapter, we have learned about the nucleation and growth. We discussed that nucleation is needed when there is a phase transformation from a parent phase to a new phase. It happens via nucleation and growth. So the whole process from one phase to another phase will have, when it's transforming, it will take some time. And hence there is a rate of transformation involved here. So so here going forward we will broadly discuss the whole frame of our discussion will be on the rate of the transformation. And as usual, since we are discussing about steel, I will like to start with the phase diagram of steel. And here you can see this is the at 0.762 or somewhere you will get 0.8 carbon concentration. We will get a eutectoid reaction where austenite will transform to alpha ferrite and to cementite, and you will get pearlite, martensite, and some other byproducts depending on which kind of treatment you are providing to the material. So so here I would like to say that around here something around 700 degree Celsius, as I already told, that the austenite will convert to its byproduct. And and on the other hand, as we have already discussed, that it will not be a spontaneous process. We need to provide some undercooling for the nucleation to start. And once the nucleation will start, and going forward growth will take place, so that there is a change in phases. So this heat treatment, whatever I'm going to discuss today in this lecture, is a very important technology. It have like a lot of application. Going forward you will get to know that it has a very high impact on the technological process that we are going to give to our product. And before going to heat treatment, I actually want to explain two very important concepts, and these are your TTT, temperature transformation curve, and CCT, continuous cooling transformation curve. And and these are actually very important because if we get to know about these curves, we will know what will be the time going to take for the transformation, number one, and number two will be what kind of heat treatment we are supposed to give to get a particular type of microstructure. So here we will start learning about this TTT and CCT diagrams. So let's see how it works. So first is microstructural and property changes in iron carbon alloys. We are already familiar with it, but still we will just do a small recap. So it says the basic concept, kinetic principles of solid state transformations are applied specifically to iron carbon alloys in terms of relationship among heat treatment and the developed microstructure and mechanical properties. As I or just so here is another very important point, like why I have chosen steel for studying the heat treatment on metals, because steel is something that gives us a number of microstructure, and there is a high possibility that it makes ideal system to study the different impacts of heat treatment. So that's the reason I have chosen this steel to explain you in this process. So let's start with the isothermal transformation diagram, or I just told you that is TTT curve, or that temperature transformation curve. So here we are considering the very basic phenomena when the austenite normally transform to perlite, which is the most probable occurrence, because if you let the austenite to cool down by itself slowly, basically there is a high probability that it will end up forming perlite. And this is our eutectoid reaction. You can see this is gamma iron, which is austenite, which can have maximum 0.76% carbon. And when I'll cool it, this is a reversible reaction on the other hand, but I'm considering when I'm cooling it down, I get alpha ferrite, and this is FeC3, that is your cementite. So here temperature will play a very important role from austenite to perlite transformation. Let's see how it happens. So here we get a curve for iron carbon alloy eutectoid composition 0.76, and you see it here versus the logarithm of time. So it's I think it's now a very familiar type of variation for you, as we have already discussed about the JMAC or Arvami equation, which that gives us the kinetics of the transformation. And here you see that we get this S-shaped curve for 3 different temperatures: 600 degrees Celsius, 650 and 675. So so here each curve data were collected after rapidly cooling the specimen composed of 100% austenite to the temperature indicated here, and the temperature was maintained constantly throughout the course of reaction. So the basic point when I say it's isothermal, we will discuss going forward, but still I'm telling you, when I say that it's isothermal transformation, the word isothermal itself means the temperature is constant. So I'm basically trying to cool the sample to a particular temperature. I mean, I'm trying to cool austenite to a particular temperature and hold the product at that very temperature. So let's see some points about about the isothermal transformation. So the family of S-shaped curves at different temperatures are used to construct the TTT diagrams. So as just we have seen, we get family of this S-shaped curves depending on the temperature we are taking in consideration, or the temperature at which we are holding our product. Number 2, obtained by isothermal or constant temperature transformation. I just explained. At low temperatures, the transformation occurs sooner, and it is controlled by rate of nucleation. Growth is controlled by diffusion is reduced. Okay. So here, like as if you remember, we have discussed about diffusion during the transformation procedure. So as so the thing about diffusion is that diffusion means I'm trying to mean the carbon diffusion. Okay, so obviously at high temperature diffusion will be higher. On the other hand, at lower temperature diffusion will be low, and this diffusion will highly impact our rate of transformation and the byproduct we are getting after the transformation. and this thing also we will see going forward how the things happen. So number 4 is that at compositions other than eutectoid or a pro-eutectoid phase, ferrite or cementite coexist with pearlite, okay, which we know that it happens, and additional curves of pro-eutectoid transformation must be included on TTT diagrams. So when I say this thing, I mean that I can get additional pro-eutectoid transformation if there will be any other byproduct alloy like cementite, alpha ferrite or pearlite or any other, maybe martensite or bainite, we must supposed to plot it on the TTT diagram. So this is how this one is our TTT diagram. This is how it looks, and I will explain you step by step, like how it is how it is constructed. So here let's start from the picture here. Here you see graph or a variation that is done by this on the basis of Gemek equation or Arbami equation, which is a S-shaped curve, and here the transformation temperature is 675 degrees Celsius. That means when I was cooling my austenite, I hold the whole sample at this particular temperature, 675, and when I hold the whole product at 675 degrees Celsius, I got this S shape. And here from the S shape, this is the beginning, the transformation begins here. That means as I have already discussed, and you must know that this is the time required for nucleation to begin, and here the growth will start and here the growth ends when the complete transformation took place. So this is my starting point and this is my ending point. So if I take the reference of the start and ending point, I got 2 points on this TTT diagram. Now if I keep on plotting like a more number of this S-shape graph or S-shape this kind of graph for different temperatures, I will get a lot of reference point, where I'll get a start where the transformation begin point and transformation end point, and if I join all the transformation begin points, I will get this red color curve which will be known as begin curve, and if I join all the transformation end points, I will get this curve. This is called this is in green color, this is called completion curve. Okay, so going forward I'll explain you the meaning, how it impacts and how can you get data or like your understanding from this curve. So let's see what it is at the middle, this blue color one, dotted one. So this one is your 50% completion curve. So, so up to here we understood that this in x-axis we are getting time, just like in the previous one. This is our time and this is the temperature. So if you see carefully this graph, you will see that on the left hand side of the this red color line or the begin curve, you see austenite, and on the right hand side of this green curve or this completion curve, you see pearlite. That means in the middle, from this point to this point, austenite is continuously transforming to pearlite. So here you see the 0% perlite, and here you see 100% perlite. That means complete transformation has took place. Okay, so this is the basically our TTT diagram, but like going forward we'll see that we can understand a lot of things from this TTT diagram, and I'll explain you bit by bit. So here the austenite in the process of transformation to perlite from left to right, and thus both micro constituents will be present during the transformation, as just I explained you. Now the rate of transformation is the reciprocal of time required for the transformation to proceed halfway to completion. Okay, so this is what the second point. This is what is designated by this dotted line. This dotted line, this blue line, it is giving the 50% completion, and the rate is given by 1 by t half. So let's see what it means. So the time required for each temperature to start the transformation, as we know that it takes some time. The other is for the transformation conclusion. The dashed curve corresponds to 50% of the formation. So it basically means that they are inversely proportional to each other. So if one increases, other will decrease. And this equation, this rate, it comes from the Jamek equation, which is given here, which is the equation number 3, which is a direct conclusion from the Jamek equation, this value of the rate of transformation. And here you see the formation of ferrite and cementite in from austenite. They are forming inside the grain, like in a dendritic manner. Say, you see how it's occurring. It's like it's just it's just nucleating. So there are again there are some constraints that comes to play in the isothermal transformation diagram. So let's see what are these. So these are this particular plot is valid only for iron carbon alloy of eutectoid composition, and for other compositions the curves have different configurations. So this is like very much expected. Of course, if I take or if I consider something else apart from this iron carbon system, or the exact eutectoid point where the austenite is transforming to its byproducts, so of course the graph will vary, the curve will change its characteristic. The plots are number 2, the plots are accurate only for transformations in which the temperature of the alloy is held constant throughout the duration of the reaction. Okay, so as we have already discussed, the main basic point of isothermal transformation is holding the product at a particular temperature, which means the temperature must have to be constant, and hence it's referred to isothermal transformation diagram, or sometime time temperature transformation plot. So let's see how this microstructure will look like at this point. So here you see it's austenite, completely solid. It's a complete solid phase, and as we know that austenite gets this side, austenite gets unstable and like start transforming something like little something near to 700, and before that you can see austenite is stable, and this is unstable phase of austenite. And but above the 727 degrees Celsius, it's completely stable. There will be no transformation at all. It's above the eutectoid temperature, but below the eutectoid temperature, yes, some transformation will take place. And here you see at the middle, when the austenite is transforming from the solid, from this type of from austenite to pearlite, you see the network of pearlite in austenitic phase, and here you see complete transformation of austenite to pearlite. So this is quite clear. So let's understand what this lines mean to us. Here, as you see, this line, this A, B, C, D is superimposed on the isothermal transformation diagram. And here AB, this one means a rapid cooling of austenite to a particular temperature, and this temperature is just above 600 degrees Celsius. Next comes BCD, this line. It's isothermal treatment at this temperature, just above 600 degrees Celsius, and you see the temperature is not changing here anymore. Time is changing, but temperature is not changing, which means I hold the this austenite for some time, for some period of time, and it's given as a horizontal segment, and time increases from left to right. Next, you see this here, the point C. The transformation from austenite to pearlite begins here, as we already know. This is our beginning curve, and after some time, which is approximately like something around 15 seconds, it reach this point D, which is correspond to the completion of transformation. So we see that how it's converting from one type to another. But here is something very interesting that we haven't yet gone through, and this is the formation of coarse pearlite and fine pearlite. So let's see what is a coarse pearlite. So at temperature just below the eutectoid, relatively thick layers of both the ferrite and the cementite phases are produced, and this microstructure is called as the coarse pearlite. So let's see what is happening here. So as we have just discussed, just below the eutectoid temperature, here thick layers of ferrite and cementite will form. As we already know that pearlite means the lamellae of cementite and alpha ferrite. And now if this each layer will be thick, it will give me something called a coarse pearlite. Going forward, we'll see the microstructure for coarse pearlite. And now let's see why it happens. So it happens because of the diffusion rate, because when diffusion rates are relatively high, such that during the transformation carbon atoms can diffuse to relatively long distances, which result in the formation of thick lamellae. As you see, the temperature is just below eutectoid temperature, that means which is quite high, and which is high temperature is always favorable towards the diffusion rate. Hence, you will get thick lamellae of this ferrite and cementite phases, which will give you something called coarse pearlite. And one more thing I want to mention, that depending on this lamellae thickness, as well as microstructure will change, and the mechanical property will also change. That we will discuss going forward what kind of mechanical property it will show. So next one is fine pearlite. With decrease in temperature, the carbon diffusion rate decreases and the layers become progressively thinner. the thin layered structure produced in the vicinity of its term and it's termed fine perlite. Okay, so it's just the opposite case of the coarse perlite. Here you see the temperature is much lower. It's something between 500 between, I mean, it's something 550 to 600. Here you see it's fine perlite is forming. That means here temperature is low, so as well as diffusion will be low, and it will form thinner lamellae or of alpha and alpha ferrite and the carbide. So here at this position coarse perlite is forming, and at this position fine perlite is forming, and the difference is the number one, the thickness in the lamellae. Number two, at the temperature of transformation. It depends completely on the temperature of transformation. And going forward, we'll see the microstructure, difference in microstructure as well as the mechanical properties. So here you see the microstructure of coarse perlite and fine perlite, and it's like quite visible. The difference is quite visible. So next is bainite. So bainite is also like is diffusional. As perlite is depends on diffusion, it forms due to the phenomena of diffusion. Bainite also forms due to the phenomena of diffusion. So here you see that in addition to perlite, other micro constituents that are products of the austenitic transformation exist. One of this is bainite. It is composed of a ferrite matrix, elongated particles of cementite, and the time temperature dependence of bainite transformation may also be represented on the isothermal transformation. So as we have already discussed when I was telling you about the TTT diagram, that if there will be any other byproduct, we'll definitely plot it on the TTT diagrams. So as we know that it's depending on the heat treatment on or the type of cooling we are providing to austenite, there is a high possibility that if we provide that kind of cooling, we will get bainite. So let's see how it is happening. So it has been, again, bainite is of two types. That is upper bainite, that is a formation after isothermal holding at temperature 300 to 540 degree Celsius, and below the nose of TTT. I'll show you what is the nose of TTT, and it basically consists of needles of ferrite separated by long cementite particles. So I hope you are very much familiar with this microstructure, as we have discussed even earlier. And this is the most common, mostly this kind of bainite forms. And the other one is lower bainite. So if you see that upper bainite forms at 350 degrees Celsius, and if you see here, we'll know that lower bainite forms at a little lower temperature, which is 200 to 300 degrees Celsius. Next, it consists of thin plates of ferrite with very fine rods or blades of cementite within the ferrite plates. So you can see here, this is you can see the needle kind of structure, and this is this pink portion is your cementite. This pink portion is your ferrite, and this needles, small needles, are your cementite. So this has been said that thin plates of ferrites with very fine rods or blades of cementite. So these are fine blades or rods of cementite in the ferrite. So this is your ferrite. Now let's see how and under which conditions it will form. So the difference between upper and lower bainite come from the competition between the rates at which the carbide can precipitate from ferrite and speed with his carbon to partition due to the supersaturated ferrite to austenite. Okay, let's see it in this way. Here you see carbon supersaturated plates, and there are two possibilities. Number one is that carbon is diffusion onto austenite. This is white phase is my austenite, and carbon is diffused in the along the and on around the austenitic phase. And then you see these plates are of carbide precipitation from austenite. This thick plates of carbon are there between the austenitic phases, and this will form your upper bainite, which will took place at higher temperature. Now what will happen if you cool the sample at a comparative lower temperature? And in this case, what will happen? Carbon diffusion on into the austenite and carbide precipitation in ferrite. So carbon is there on the austenite as well as carbide precipitation in the ferrite. These are your cementite, these needles of cementite, and then it will give you this kind of structure. Here you see this carbon layers and cementite needles in the austenitic phase. So this is what makes our lower bainite that took place at low temperature. So let's see how it will this will look at on the isothermal transformation diagram when we will put the bainite on it. So here one thing I want to mention this there is something called a nose of the TTT transformation. So a nose is nothing but, here you see the and we already know that from the rate of transformation that the rate actually first it increases and reaches a maximum, and then it goes sluggish, or I can say that it gets slow after some time, but first it increases and reaches a maximum. So the point where the rate of transformation is maximum, we call it as the nose of the TTT diagram. So this is the nose of the TTT diagram, and there is and here you see A is austenite, P is perlite, and A is again austenite, and B is bainite. Fine. So here you see this austenite to perlite transformation is occurring above the nose of the TTT diagram. On the other hand, the transformation from austenite to bainite will always take place below the nose of the TTT diagram. So here I want to mention that normally if you normally perlite will form if you cool down the sample and hold it something near 540 degree Celsius. Here 540 degrees Celsius, if you hold it something here at 540 or above 540, you will get perlite. But if you hold it below this 500 below 540 to up to 200, you will always get bainite. As we have already discussed that from something around 300 to 540, if you hold the austenite from 300 to 540, you will get upper bainite, and if you hold it from 200 to 300 degrees Celsius, you will get lower bainite. So these are the temperature ranges of transformation, and here I want to mention a very interesting fact that the transformation of austenite to perlite or bainite is actually a competitive procedure, because here, as I said, both have a temperature limit. The upper bainite and the perlite both have a temperature limit of 540 degrees Celsius. So depending on various physical parameters, it will be a competitive process that if the exactly at this temperature if the austenite will transform to perlite or bainite. So, so we are done discussing about bainite. Let's see what all the other byproducts it may can give depending on the the cooling temperature. So that is another byproduct is now spheroidite. If a steel alloy having either perlitic or bainitic microstructure is heated to and left at temperature below the eutectoid for a sufficiently long period of time, and the temperature will be something around 700 degrees Celsius. And it's example that since it's below the eutectoid temperature, for example, I'm taking this 700 degrees Celsius and I have cool it for a long period of time, which will be something around 18 to 24 hour. Another kind of microstructure will form and we call it as spheroidite. So what is special about spheroidite? The specialty is that the carbide phase appears as sphere-like like particles embedded in a continuous alpha phase matrix that you can see here. These are your this sphere-like cementide phases that are embedded in this alpha matrix, and this transformation has occurred by additional carbon diffusion with no change in composition or relative amounts of ferrite and cementite present. So this is our spheroidite, and next is martensite. We know what is martensite, but the interesting thing is that since all of the other byproducts forms with the process of diffusion, martensite is something that the transformation of martensite is a diffusionless process, and we will see how it happens and why it's a diffusionless transformation. So martensite is a non-equilibrium single-phase structure that results from a diffusionless transformation of austenite. And no thermal activation is needed during austenite to martensite transformation, and it is also called an athermal transformation. So let's see what happens here. So this is my martensite, and it's quickly cooled or it's quenched. So it's quenched up to a particular temperature, and this hasn't even touched the nose of the TTT diagram. It just quickly cooled and hold it, and we hold it after quickly cooling it. We hold it at a particular temperature, and the thing is that this quenching the martensitic transformations occurs when the quenching rate is rapid enough to prevent carbon diffusion, and if there will be any diffusion, however, will result in the formation of ferrite and cementite phases. Since the martensitic transformation does not involve diffusion, it occurs almost instantaneously. And you see that like this is the mechanism how it's forming. The martensitic grains nucleate and grow at a very rapid rate, and since the martensitic transformation is diffusionless and instantaneous, and it is not depicted in the diagram as it is like perlite or bainite. So here you see we can like for perlite and bainite we put it on this curve, but martensite is like drawn separately, and this is the reason why it has been done. So here you see that there is no effect of time on this, like no effect of for how long you are holding it. See, this curve is the horizontal line. That means the transformation rate will be same for however long time you hold it. and we'll see it in the next slide again. So it's actually a summary of all the kind of microstructure we are getting. Here you get coarse perlite just below the eutectoid temperature, and above the nose of the TTT diagram you get fine perlite, and just below the nose of the TTT diagram you get upper bainite, and at a certain temperature, something around 200 to 300 degrees Celsius, you get lower bainite. And here at this position, at quite lower temperature, it's a quite lower temperature, you get this martensite. So let's see here the same diagram. It is also, so here you see at something above this 200 degrees Celsius, something around 220 degrees Celsius, you get the martensitic transformation just begins. So it just started, and here something around it will be something around 170 degrees Celsius. It's the martensitic transformation is 50%, and here is the 90%. So the basic point about this horizontal line is that there is no effect of time on the formation of martensite. If I hold the temperature after crossing the M start, which is at 220 degrees Celsius, as soon as I cross this temperature, it will start forming. And next, suppose I'm holding it at 200 degrees Celsius for a certain amount of time, the amount of martensite which will form will remain same. Now let's consider this 50% thing, which is at 170 degrees Celsius. There will be 50% of martensite, and if I hold this temperature, it is going to be 50% only without any effect of time. The quantity of martensite the quantity of the formation of martensite will depend only on temperature, not on time. It's a very important point. And on the one more thing I want to mention, that martensite is also a metastable phase. So this is basically the conclusion of our TTT diagram, is that number one, from austenite phase, okay, so it forms from the austenite phase, we know it, and cool it to desired temperature. You have to cool it to desired temperature. Number two, hold the specimen at a temperature, and note down the time at start of the transformation and end, and you can use dilatometer. So, and dilatometer is actually an instrument that will give you the change in volume or dimension of the sample. And so dilatometer to determine start and end transformation, and we know like how to plot the diagram. So we are done with our isothermal transformation or TTT diagram. So next is our continuous cooling transformation diagram. So you must be wondering that when we already have this TTT diagram, why we need this continuous cooling transformation diagram. So let's study about it. So here you see a continuous cooling transformation phase diagram is often used when heat treating steel. These diagrams are used to represent which type of phase change will occur in a material as it is cooled at different rates. These diagrams are often more useful than time temperature transformation diagrams because it is more convenient to cool materials at a certain rate than to cool quickly and hold at a certain temperature. Okay, so why it has been told that it's more convenient to do this continuous cooling? Because if your sample or the product is small in size, it's easy for you to cool down the sample and hold it in a particular temperature. But what if you have a very large piece of sample, you have a huge piece of sample, for example. In such case, mm, it's not easy to hold the sample at a particular temperature, because the surface of the sample will be at a particular temperature, and which will be lower because the surface cooling will come to play. On the other hand, the core of the material will be at high temperature. That means you will not be able to like hold the whole sample at a constant temperature, because your surface is at a different temperature and the core of the metal is at a different temperature. Hence, in the manufacturing plants, when they deal with a huge piece of sample, they normally use this continuous cooling transformation curve. So let's see next how it comes to play. So here you see that a, a, a continuous cooling curve is, this is the dotted lines are your isothermal transformation, this your isothermal transformation curves, and these rigid curves are your continuous cooling transformation curves. So the first point that we can see that when we transfer from TTT to CCT, the curve has shifted towards a little in the right hand side, and on the other hand you can see one more thing, that our CCT curve has stopped here. It is not extended like isothermal curve. The isothermal curve is extended, but this continuous cooling transformation curve is not extended. It's finished. It's closed here. And as usual, like the previous one, this is the temperature and this is the time variation. So thus the isothermal curves are shifted to longer time and lower temperatures, as indicated in this figure. As you can also see, I just explained. For an iron carbon alloy eutectoid composition, a plot containing such modified beginning and ending reaction curves are termed as. So okay, here we have, as I told, this is the same thing. So let's see what are the other aspects of this continuous cooling transformation curve. So next one, in figure 5.11, you see the moderately and moderately fast and slow rates of cooling are superimposed and labeled for eutectoid steel. So this blue line is your slow cooling, and heat treatment associated with this one is full annealing. We'll study going forward. And next one is moderately rapid cooling curve, which is normalizing, which also we are going to study, which are heat treatments. So this one is your slow cooling rate, and this is your moderately rapid cooling. And this is my CCT curve. This is the beginning curve and ending curve, and this is the nose of the CCT transformation diagram. So here you see that when you do slow cooling, the byproduct is your coarse pearlite, and when you do this moderately rapid cooling, you get fine pearlite grains, because this cooling rate has crossed both the starting point and the ending point. So I'm getting fine pearlite, and here I'm getting coarse pearlite, which means that the type of microstructure we will get definitely depends on the cooling rate, because here cooling is happening, like the process of cooling is continuous. We are not holding the sample at any particular temperature, but we can control the rate of cooling, that if the cooling will be fast or slow or moderate or whatever it is. And one more very important thing I want to mention here, that you must be wondering that the TTT diagram was extended up to longer, up to this long, and it was extended to more temperature zones, but the CCT diagram is closed here. But so what is the reason why it happens? So the basic reason for this thing is that if you do continuous cooling of austenite for steel, that is iron and carbon system, where there is no other alloying elements are mixed, you will never get bainite. That means bainite will never form. So this bainite will not form when an alloy of eutectoid composition is cooled continuously to room temperature. This is because all austenite will have transformed to pearlite by the time the bainite transformation has become possible. It means by the time this temperature will come down, or to the particular temperature at which the bainite form, by the time it will reach this temperature, all the austenite will be already transformed to pearlite. So there will be no room for formation of bainite in this case. And here you see AB is the nose, and as I said, the nose is the point where the transformation rate is highest, and and this is so this thing you have to keep in mind, that if there is no alloying element, there will be no bainite formation in the CCT diagram. So this is the thing, and this is about your your CCT diagram. And there is one more aspect of your CCT transformation, is that, so how about forming the martensite? We see that martensite is forming, but how? The thing is that the thing about martensite is that when you cool the sample in such a way that it skip the nose, and in such case martensite may can form, and this is all about your continuous cooling transformation diagram. And here, as I told, if you mix some alloying elements, there is possibility that bainite will form. This is your cooling curve, and here you see bainite is formed. So this bainite is formed in the steel in presence of 2% of manganese in the steel. So here we have seen that there are some few points that I have collected together about the CCT diagram. CCT curves does not extend beyond the nose of TTT curve, and I explained why. And one cannot obtain bainite microstructure by continuous cooling. We will get plethora of microstructure due to continuous cooling. Now you must be thinking how. As we have discussed, that when you have a big piece, because we are normally using this continuous cooling for a huge piece of our sample, so at different layers of the sample, the cooling rate will be different. So obviously at surface, the cooling rate will be very fast. There will be, it will easily get cooled. On the other hand, at the core of the material, the cooling rate will be slow. Now, depending on the slow and depending on the cooling rate, obviously my microstructure will change. So it may be possible that on the top of your sample you have a different kind of microstructure, and at the core of your sample you have a different kind of microstructure. And this is what I mean by we will get a plethora of microstructure due to continuous cooling within the same sample. Number 4 is that to get martensite, we have to avoid the nose of the CCT diagram. As I already told you, you have to cool it continuously, but we have to avoid the nose of the CCT diagram, and then you can get martensite. So with this we have covered a very important technological aspect of material science and engineering, and going forward in the next video lecture we will learn about the mechanical properties as well as the heat treatment of the different steel grades. Thank you so much.